Okay, so if there are no more questions, let's continue with this and let's see why, I mean, how we can show or how does it work more or less that, well, I mean, how we can prove that there is indeed an infinite number of states at infinite distance. Okay, so the key ingredient to do this is the monodrome transformations that I was also discussing with Wolfgang. And so the idea is that these periods, okay, that are determining both the Keller potential and the mass of the BP states transform when you go around the singularity. They undergo a monodrome transformation. Okay, so when we go around, it changes by this matrix. Okay, and then it's going to be very important whether this transformation is of finite or infinite order. So whether it goes back to the same situation. So whether there is some n such that t to the n is the identity, or whether you can never go back, okay, to the same situation. So there is no n such that this is the identity, and then this is called infinite order. Now, from the point of view of the effective field theory, these monodrome transformations represent the axionic shift symmetries. Okay, so we have some axions, and the discrete shift symmetry is inherited from these monodromes. So they are sort of redundancies of my theory. And what we can prove is that in order to have an infinite distance singularity, you need to have an infinite order monodrome. And this is done by using the nilpotent orbit theorem of Schmidt. Okay, so this is a theorem which is very useful because, I mean, the traditional approach, I would say, would be to take a specific Calabi-Yau and then compute the periods and see what happens. But thanks to these theorems of limiting Hodge theory, we can provide some universal expansion for these periods at any asymptotic limit. So whenever we approach one of these boundaries, that is valid for any Calabi-Yau, okay? So the information of the Calabi-Yau is just encoded on this finite part, but the dependence on the moduli, okay, on this moduli that we send to infinity, is encoded in terms of this factor that depends on these monodrome transformations. So n is a nilpotent operator that we compute in terms of the log of t, and it's nilpotent because t is a unipotent matrix. Okay, so just using this universal expansion, we can easily see that if you plug it into the Keller potential, the Keller potential to leading order near this boundary is going to be just some polynomial on in the imaginary part of C, which is what I call the axion, and the real part would be the axion. Okay, so it's a polynomial of degree d, where d is this effective nilpotency order. Okay, that depends on the properties of the monodrome. So it's not the space-time dimension. Okay, it's this nilpotency order. And just the fact that to leading order we have this polynomial expression, and that this is just corrected by exponentially suppressed corrections, tell us that the metric near these points is going to be d over 4 imaginary part of c squared, which means that when you compute the proper field distance, it diverges logarithmically. Okay. And if we plug this on the mass of the BP states, is e to the k half, is going to give rise to some expansion, the charges in terms of these coordinates. And if we take just the ones that are becoming massless, we can see that indeed, since this is a polynomial expansion and the proper field distance goes logarithmically with this coordinate, the mass is going to decay exponentially in terms of the proper field distance, where this lambda, this exponential rate, is fixed by the properties of the monodrome transformation. Okay, so this exponential rate is bounded this nilpotency order. And we can use this to classify the possible limits that you can have in a given Calabi-Yau, and therefore the possible exponential rates of the tower that you can have as well. And well, there has been a lot of words about this, but for example, in a Calabi-Yau threefold, it's very simple because this main type of the singularity is upper bounded by the dimension of the Calabi-Yau. So in this case, it's going to be 1, 2, or 3. So you just have these three possibilities, which means that the minimum value that you can have for these Calabi-Yaus is 1 over square root of 6. Okay, for the BP states. Okay, so now this is to show the exponential behavior, but you really have to show that there is an infinite tower of 10 and not just a few of them, as we discussed. For this, I'm going to refer you to the papers because it requires more work. But basically, the intuition is that since we have a monodromy transformation that is of infinite order, this monodromy is also going to populate an infinite orbit. So an infinite number of states that transform and that they will become massless at the infinite distance point. Okay, so by acting with this monodromy on some seed charge, you can populate an infinite number of them, an infinite tower, and you have to show that indeed they really count as VP states in the sense that well, you have to take into account all the words of marginal stability, and so what we show is that the number of VP states is actually increasing exponentially as you approach the infinite distance point, and you get infinitely many only at the singularity. So this is the way this is proven. And also let me emphasize that in these cases, for example, there are two global symmetries that would be restored at the infinite distance limits. We have a continuous version of this monodromy, so these axionic discrete symmetries can actually be promoted to a continuous one at the infinite distance limit. So it's a zero form global symmetry and also the dual two form. And then we also have some global symmetry coming from the gauge coupling going to zero of the gauge field. So what happens also here is that the gauge coupling goes to zero. So indeed, these states, not only the mass goes to zero, but also the charge in a way that they are extremal and they are consistent with the weak gravity. And we would also restore the typical U1 global symmetry. And therefore, we can also understand this value of the exponential rate in terms of the black hole extremality bound. And we can compute and check that it works. Okay.
Sorry, can I ask a question?
Yes.
So I think I'm repeating my question. In these, you had two implications. First, that infinite distance goes to infinite order, then infinite order means infinite number of particles. In both of these, does the arrow also go in the other direction?
Okay, yeah, so I didn't put it here precisely because, yeah, it's not so trivial, let me say. So the fact that infinite order implies infinite distance, it's something that has been conjectured by the mathematicians, but has not been proven because it becomes, I mean, all the path, there are many path dependent issues that become complicated in that case. You have to show that really all the trajectories. I mean, in order to be at infinite distance, you need that all the trajectories have infinite length. So, I mean, it's much harder to prove than the proof that I show here, that is only the other direction. So it has been conjectured by them, but has not been proven. Now, in all the examples that are known, it's always the case. I think it's just a matter of, I mean, that is more technically involved. But I mean, just to be clear, it has been conjectured. If we combine this with the emergence argument that I was telling you about integrating out, then we can give, if you wish, like a motivation for the mathematicians. So I mean, we can tell them that indeed, if we understand the complex structure moduli space as quantum in nature, as taking into account all the effect of integrating out these BP states, it shouldn't be possible that we get infinitely many at finite distance. But that's a physics perspective, and the mathematician perspective has not been proven yet.
So somehow you're kind of avoiding an essential singularity, right? You don't want to pile up of all these new particles at something like that.
Yeah. Yeah. So it's something, yeah, let me put it here. It's something that's, I mean, the proof is still missing the complete proof. It has been proven, for example, for 2 moduli. I think out of 2 and 3 has also proven, but not in complete generality. Okay. Also, just, I mean, to be, it's a bit, it's just related, but to be completely clear, it's important when I see here the infinite order, it's important that it's satisfying this, so that it's not annihilating the period vector. So what happens, for example, in the conifold point, which is at finite distance, is that this monodrome is actually of infinite order, but it annihilates the period vector so that the d is equal 0. So it's like, it's as if you don't have an infinite order monodrome. Okay, so just to be precise. Okay, so just a few words about the hypermultiplet moduli space. I mean, I cannot cover everything, so I chose to cover the vector multiplets, but there's also works that are done in this hypermultiplet moduli space. In this case, we don't have PP states, we don't have PP particles, but we have charged strings that are becoming tensionless, and we have KK towers. And what happens is that one has to be very careful because the limits can be obstructed by the quantum corrections because this moduli space is not so protected. But when that happens, these quantum corrections always force you to move along some direction in which there is a string that is becoming tensionless at the same rate than the KK tower. So it's one of these string perturbative limits what arises. Okay. And the other example which I want to discuss in more detail is the case of 5-dimensional n equals 1 theories. So in this case, we focus on the Kähler moduli space of M theory and a Calabi-Yau threefold. So from the perspective of M theory, we are going to get towers of wrapping M2 branes, which corresponds to tensionless strings from the perspective of 6-dimensional F theory compactifications. Now, there are 2 possible approaches. One is to borrow the classification of singularities that we had before, based on the monodromies and so on, that now are going to act on the M2 charges. But I want to discuss this other approach, since it has also led to very interesting connections in mathematics, which is based on what is the geometry that arises in these asymptotic limits, more specifically in terms of what is the vibration structure of the limits. So you have, I mean, the limits that are going to be considered here, that you have some fiber that is going to shrink to 0 size, and that's going to be at infinite distance, and then you can classify the possible limits that you have in terms of this vibration structure. And in particular, for this case, it has been shown that, well, these are the 3 possible cases. It can be a T2, a T4, or a K3. And just for the, I mean, for simplicity, and because sometimes it's bad if I try to cover too much, I'm going to focus just on the case in which it's a K3 fiber, which was also the original work that was studied. Okay, so the physical setup is that we have some 7 branes in these F theory compactifications that are wrapping some divisor, and we are going to have some gauge field theory coming from these 7 branes. Okay, so contrary to the previous case in which we were just talking about the closed string sector, now by going to F theory, we can also talk about the gauge fields that come from the open string sector. And the question is, what happens if you try to make one of these gauge couplings of these gauge fields very small? So the gauge couplings for this gauge field theory is proportional to the volume of the divisor that the membrane is wrapping. And the limit the one is interested in is a limit in which this volume goes to infinity, so that the gauge coupling goes to 0. But the volume of the base remains finite, so that the Planck mass remains finite. Okay, so the interest here is to understand what happens with limits that have nothing to do to the compactification. Okay, so what about some limit? I mean, how string theory serves the day when we take a limit in which the Planck mass remains finite, so we are not going to grow extra dimensions, and what we do is to shrink some cycle and go and make, well, in this case, like make this divisor large, so the gauge coupling is going to be small. And the answer that string theory gives for us is that when you try to do that, this is only consistent if there is another curve, C0, that intersects non-trivially with C, and the volume instead goes to 0. And if that's the case, the resolution is very nice, because then I can have some DC brane that is wrapping this curve C0, and then the tension is going to be proportional to the volume of this curve. So what happens is that when we try to engineer some situation in which the Young-Mills coupling goes to 0, then there will be a DC brane, a string coming from a DC brane whose tension goes to 0 and gives us the infinite tower of states. And in this particular case of the K3 fiber, one can dualize this situation to show that this string is nothing else than the critical heterotic string on K3. Okay, so I wanted to mention this works also because, yeah, as I said, it has triggered interesting connections between algebraic geometry of the Calabi-Yauns and modular properties of quasi-Jacobi forms. If you are interested in the details, we have here Wolfgang, so I'm sure he can answer any question. But just to give you an idea, the point is that we can use these modular properties of the Jacobi forms of the elliptic genus to determine the spectra, because to say that we have a string that is becoming tensionless is not enough to show that you really have an infinite tower of states. I mean, you have to quantize the string and show it. And in this case, it can be shown for these critical strings. And the excitation spectrum that one gets preserves these equations that I put here. So for each excitation level of the string n, we get these states with this mass and charge. So if we combine it, actually put it in a more convenient way. So what happens is that the charge of these states goes as the mass plus some quantity. That depends also the gauge coupling, where this m is this intersection number. And this is always bigger, right, than the mass, which would be the would correspond to the extremal value of black holes in that theory. So what one gets in this scenario is a sublattice. It's a sublattice because there is this index here. Okay, so one only gets a sublattice of states that is satisfying the gravity conjecture and is strictly satisfying the gravity in the sense that they are super extremal in general, which is what one would expect since they are actually non-BPS excitations. So it's also consistent with this sharpening. So this is one of the few evidences that we have for non-BPS states. Okay, and this can be extended to other fibrations and also to n=1 four-dimensional theories, in which maybe I should remark that it's not so clear that one gets the sublattice. So I think this is a potential candidate to understand better what is the structure of the tower. But well, anyway, I mean, it works sort of in a very similar way, but in even, I would say, more non-trivial than in this case of the heterotic critical string. Okay, any question? Okay, so let me just say a few words about n=1 for D. I'm not gonna say much because I want to spend the rest of the time discussing a bit the other conjectures, but just to give you some flavor of what we are doing this year. We are trying to extend right now all these works to n equals 1 4 dimensions, both taking all the perspectives that we can think of. And the point is that in this case, there are no BPS particles, so it's more difficult, right, to keep track of the states that are becoming light. But we have BPS strings and also BPS membranes. And I think that's great because that's already telling us a lot about effective field theory. So, for example, the field metric is parameterized, so if you wish, is equal to the two-form gauge couplings when I have some strings. Okay, so if I have some BPS strings, one can show that they are charged under some two-form gauge field, which is dual to the actions, and they parameterize the field metric. And for the case of membranes, they are going to be charged under some three-form gauge field, whose field strength is dual to the fluxes that I am adding. And then the charge, the gauge coupling, and therefore the charge of the membrane is parameterized in the flux potential. So we can translate information and conjectures about the field metric and the potential to properties of the strings and the membranes, of these BPS strings and BPS membranes. And in particular, well, it seems in all the string theory examples that we have checked, it seems that there is always one can find always some string, some axionic string that is, it's magnetically charged under some action that is becoming light at every infinite distance limit. And we have conjectured that this is the case also based on some bottom-up motivation, studying the back reaction of the strings and the RG flows. And whenever this string satisfies the gravity conjecture, then it's automatic that the tension of the string is going to decay exponentially in terms of the proper field distance. So this is something that we have proven in this paper. And the same lower bound that we have before in terms of extremality bound of black holes for particles also works here, but in terms of the extremality bound of these strings. Yeah, so the situation is quite similar, just we need to think of other objects and consider more general limits. But there are many things to know. I hope we will improve our understanding of n equals 1 in the future. Okay, any question? Okay, so before going to the other conjectures, especially due to the questions that we had, let me mention a bit what is this emergence proposal. So all the string theory evidence that I gave you so far, in one sense it's very nice because we can provide quantitative tests and understand what is underlying these conjectures, whether it's a matter of supersymmetry or whether it's a matter of having these discrete symmetries or what's going on. But of course, it's more model dependent, no? In the sense that we focus on large classes of string compactifications. We can never be sure if it's not just a matter of the lamppost. So there is one proposal that tries to provide a more bottom-up explanation for the weak gravity and the distance conjecture together, which is based on the idea that the relations that we observe with the weak gravity and the distance conjecture, right, that are relating the mass of some tower of states with properties of the effective field theory, like the field metric or the gauge coupling and so on, that these relations is nothing more than some rules that appear from renormalization group equations. So that's, we already know, right, that when we integrate out things, that we are going to get some relations between the renormalized couplings and the mass of the states that we integrated out. So the question is, maybe is this all we are observing with these conjectures? That this relation is nothing magical, but it's just can be understood in terms of integrating out the towers. And the proposal is that all the kinetic terms in the effective field theory emerge from integrating out these massive states up to the quantum gravity cutoff. So that the fields are non-dynamical in the UV and all the dynamics emerges in the IR. Now, this changes the arrow of the conjectures, in the sense that instead of saying that when you have small gauge couplings or infinite field distance, you are going to have infinite tower of states that become light, is telling you that whenever at some point you get an infinite tower of states that become light, then you are going to induce in your effective field theory some small gauge coupling and some infinite field distance. So that's also the way to show that BPS, only a finite number of BPS states can lead to a finite distance in the IR. Now, instead of showing this in detail how it goes, I'm going to leave it as an exercise because it's an easy toy model quantum field theory computation. But you can actually check that if you integrate out a tower of states up to the species bound that I gave you yesterday, so that remember that the species bound is some cutoff, right? That is the quantum gravity cutoff that is smaller than the Planck mass when we have a large number of light states. So whenever we integrate out the tower up to this species bound, which is going to go to 0 when we get more and more states. So it's not a constant cutoff, but it's a field-dependent cutoff, and that's very important for the computation to work. One can show that the one by taking into account the one loop contribution from integrating out this tower to the gauge coupling and the field metric, one obtains precisely the relations that the weak gravity conjecture and the distance conjecture tells you that should hold. So one obtains that the mass of the states behave as the renormalized gauge coupling, and that the distance behaves logarithmically in terms of the mass. And in order to do this, I didn't have to specify any specific behavior of the mass. I just need to be able to integrate a tower up to the species bound. Okay, so you can do this as an exercise, and if you have questions, I would be happy to answer in the Slack. Okay, so for the next 20 minutes, we're going to complete this map of conjectures that I gave you yesterday at the beginning. So these are the conjectures that we have studied so far. And from this, actually, we can generalize and obtain some extensions that constrain not just the kinetic terms, so not just the gauge coupling or the field metric, but also the scalar potentials and the vacua that we can have in the landscape. Okay, there are no questions, right? I can go on. Okay, so the first conjecture I want to discuss is what I call the ADS instability conjecture, or non-SUSY instability conjecture, which says that any non-supersymmetric vacua should be unstable, meaning that it's at best metastable. So it could be that it's perturbatively stable, but it should be then non-perturbative unstable, it should be able to decay to some lower minima. So that the only way to protect a vacuum from decay should be supersymmetry. That's basically what the conjecture says. Okay, so the motivation is twofold, or at least there are two ways to try to prove this. One comes from the weak gravity conjecture for the case in which this vacuum is supported by fluxes. Okay, so whenever I have some gauge fields in the internal dimensions, okay, these are the fluxes from my effective field theory. I can dualize these fluxes to some top form gauge field. Okay, so in 4 dimensions, some F4, and we can apply the weak gravity conjecture to this top 4 gauge fields. And the conclusion, I mean, if we apply the weak gravity conjecture, it should tell us that there should exist some charge d-2 brane, so some domain world, some codimension 1 object with a tension that is smaller or equal than the charge. Right. This was the weak gravity conjecture. We can obtain the same result if we apply the weak gravity to the original fields in the internal dimension and the dimension reduce. So this branes that should exist behave as domain walls that interpolate between different vacua with different values of the flux. Now, if we assume this sharpening of the weak gravity conjecture that I told you yesterday, meaning that the weak gravity can only be saturated if the state is BPS in a supersymmetric theory, then this imposes non-trivial constraints and non-trivial implications for the stability of the vacuum. Why? Well, because if the vacuum is not supersymmetric, then the weak gravity tells you that there should be some domain wall with a tension which is strictly smaller than the charge. Okay, it cannot saturate it. And if the tension is strictly smaller than the charge, then it behaves as a bubble instability in ideas. So, in particular, for example, in this paper of Maldaceno, one can construct the instanton solution that will mediate this decay. So you write the dBi axiom for a spherical brane and solve the Euclidean equation of motion and obtain that the radius for this bubble, okay, is equal to the ratio of the tension over the charge. So only if the tension is smaller than the charge, there is a solution with a finite value of the radius. So this really becomes a bubble that will expand. I'm not going to do here the derivation because then the time I would eat all the time, but I can give you some intuition of why that happens. So if the tension is smaller than the charge, the cost of energy of expanding the bubble is going to be smaller than the gain in energy that you have from the electric repulsion between the different points of the wall. This is something that only happens in ADS because in Minkowski, for example, any tension would give rise to an instability because the volume will always grow bigger, no? It will be bigger than the surface. So the cost of energy of expanding the bubble is always smaller. But in ADS, you need to satisfy that the tension has to be smaller than the charge. So if your vacuum is supported by fluxes and this sharpening of the weak gravity conjecture is true, so that it can only be saturated for BP states, then automatically the weak gravity conjecture is telling you that non-supersymmetric ADS should decay. Okay.
May I ask a question?
Yeah.
Yes. This conjecture, is it a dynamical statement or is it a equilibrium comparison of free energies? In other words, are the boundary conditions of the two things you're comparing, are they the same or are they different?
Are they the same?
They're the same.
Are they? Yeah, they have to be the same.
I see. So when you say it decays to less flux,
yeah. So when I say I break supersymmetry, yeah, and also when I say that we are breaking supersymmetry, I'm thinking of not breaking supersymmetry with the boundary conditions, but breaking supersymmetry locally in the bulk. Otherwise, it's not clear that this has to happen.
I see. So it has less flux, but somehow the same cosmological constant.
Okay. Well, maybe it depends. Yeah. Well, the thing, it's always with the vacuum decay, right? Like the bubble is going to expand up to infinity. So in the end, it's like a forced vacuum decay. But of course, I mean.
So that's a dynamical statement. So you get an ADS with a different lambda
statement. Yeah, exactly. You get so inside of the bubble, you are going to have an ADS vacuum which has smaller energy, smaller vacuum energy.
So it's not just a comparison. It's not kind of in the same. You fix boundary conditions in one theory and then compare to vacuum. It's not like that.
No, okay. I was thinking of other boundary conditions. Yeah. In that sense, yeah, you have to decrease the vacuum energy. Yes. If you don't decrease it, what's going to happen, for example, is that you have some straight domain wall, right? Okay. Now, the other option is that, for example, if you don't decrease the energy, what happens is that you can decay to nothing. And this is also the other motivation. Well, don't know if it was a motivation because something we have discovered a posteriori, but you can also a posteriori motivate this conjecture from the existence of bubbles of nothing. So how this works? Well, bubbles of nothing is a more exotic instability, if you wish, in which the vacuum, instead of decaying to another ADS with less flux, is decaying to nothing. So the vacuum annihilates itself. And this is possible because there are some compact dimensions that are shrinking to 0 size at the wall of the bubble, so that the full solution is actually regular and geodesically complete and everything is fine, and it describes an instanton, some instability of your vacuum. So the bubble of nothing can exist whenever you are able to shrink some compact manifold to 0 size. And I like these instabilities because I think they have the potential indeed to provide a universal instability whenever you break supersymmetry, regardless of the specific details of your compactification, as long as you have extra dimensions, okay? As long as you have some compact space. So how it works? Well, the thing is that, I mean, we can understand better what is this requirement, okay? That the compact internal space has to be able to shrink. And if this is possible, then we say that the bubble is topologically allowed. Okay, it's like the same abstraction that we have to build. So let me explain how it goes. So the idea is that this bubble of nothing is topologically allowed. So the compact space will be able to shrink if this compact space can be written as the boundary of another manifold. Okay. Why is this? Well, if you think, so for example, the easiest example is the Witten's bubble of nothing, in which what we have is just some Kaluza-Klein compactification on a circle, and then the circle goes to 0 size at the wall of the bubble. So we have this cigar structure, which we have some circle with some finite radius at infinity that goes to 0. So the fact that we can do this, that we can shrink the circle, is because we can fill this circle, right? So we can understand this circle as the boundary of this disk, of this cigar. So it's just equivalent to say that we can shrink it, that to say that it's the boundary of another manifold. And if you remember from yesterday, it has already been classified when this can happen, and some manifold is a boundary of another one whenever it belongs to the trivial class on cobordism group. Okay, so this is this bordism group. Okay, so if you remember from yesterday, two manifolds belong to the same class in bordism group if the reunion is the boundary of another dimension of another manifold of one dimension more. And if you belong to the trivial class, it means that that manifold is a boundary by itself, right? And also from yesterday, remember there was this Swampland conjecture based on the absence of global symmetries, which told us that, which claim that the cobordism group of quantum gravity should always be trivial. So that everything should belong to the trivial class, meaning that there is no topological abstraction to construct bubbles of nothing. So that any compactification that you can think of should be able to shrink and generate a bubble of nothing. Okay. Now, of course, I mean, this is the conjecture, but in fact, we have used this to show, I mean, to generalize this Witten's bubble of nothing of the circle to more general dimensions, in which, I mean, the manifolds are even consistent with a periodic spin structure. So it's even consistent with having supersymmetry restored at some scale. And we saw that precisely because the bordism group is 0 in those cases, one can construct a bubble of nothing as long as the vacuum breaks supersymmetry. So this is an important point, is that, I mean, even if this absence of global symmetries can motivate that you can always topologically construct this bubble of nothing, it doesn't tell you anything about the dynamics. So there could still be some dynamical abstraction for the bubble to expand. So it's not really a bubble, but it's an end brane, as we discussed yesterday. And whether you have this dynamical obstruction or not is associated to whether your theory satisfies some particular local energy condition. For example, if we don't have charged fermions, this condition is the dominant energy condition. If we have fermions, charged fermions, we have seen that this condition seems very similar to the weak gravity conjecture. So I think this is very exciting because there are more things to understand, and I think maybe understanding these local energy conditions better, we might be able in the future to provide a proof about the fact that any non-supersymmetric vacuum should be able to decay. Okay, any question?
Maybe I will ask one. So we,
Yes.
in the context of ADS CFT, we know a few high-dimensional non-supersymmetric CFTs. They're not CFTs with weakly coupled gravity duals. But is there still any lesson to learn? Or in other words, imagine that the theory of the gravitational theory is not weakly coupled. Do these conjectures still tell us anything? And I don't know, I'm thinking about vector idealizing, which makes sense. We know they're stable, non-perturbative.
Yeah, exactly. So no, thanks for the question. It's something I really need to remark now. As you already pointed out, this weak gravity and all these conjectures only applies if we have a weakly coupled Einstein gravity description, which means that if we have a non-supersymmetry CFT, right, as we have this non-supersymmetry CFT, the only implication that it gives you is that it cannot have an ADS dual which is weakly coupled to Einstein gravity, so it cannot have a large N or a large gap. That's just for the students. The point is that if you have an instability in the ADS bulk, this, from the point of view of the bulk, might be fine. Well, in ADS you have problems, but in general you could say, okay, it's very exponentially suppressed, so nothing doesn't matter. But if you are from the point of view of an observer in the boundary, this happens instantaneously because an observer in the boundary has access to an infinite volume of the bulk. So the CFT is not well defined to start with, which means that's what we said, that non-supersymmetry CFTs that are unitary and well defined cannot have these ADS duals. Apart from this, I don't think there is any other implication as far as I can think of.
Yeah, I guess this is a sort of intuitive when we talk about the spectrum of particles and something like the gravity conjecture, but here you seem to have something more topological, and so one might wonder if this is less sensitive to.
Yeah.
But okay.
No, yeah, I completely agree. Yeah, I don't think this is the end of the story. Okay. Also, now with this relation to the cobordism group, right, and this topological obstruction and so on, this should be a way to understand different.
Yeah, maybe I guess.
And the interfaces.
Maybe I can some concrete, but question something like why is it that in Vasiliev theory we do not have bubbles of nothing? Something like this, because Vasiliev theory dual to vector away and it's not supersymmetric.
Yeah, exactly. Okay. Yeah, the thing is that the absence of global symmetries, so far, it's only clear if you have also an Einstein gravity dual. So it could be that all this issue of the cobordism group, one has to be very careful when to apply it. And maybe it doesn't apply to these Vasiliev theories. It would be nice, actually, it would be nice to check what is the cobordism group in that case. And maybe it's non-zero and there's no way to kill that class or something like that. Otherwise, the other solution is related to this dynamical obstruction and the energy conditions that are satisfied in Vasiliev. But yeah, it would be something interesting to check more. I'm sure that there is a way to think of this more generally in terms of the CFT and understand what happens and doesn't happen, and what is the relation with the large N and large gap that makes that possible or not possible.
Right.
Okay. Yeah, so this is one of the things I wanted to discuss. And let me also just super quickly, because we are running out of time, not only for the ADS, but actually one can show that this conjecture has implications for the standard model of particle physics, because compactifications of the standard model also can give rise to non-supersymmetric ADS vacua. And if these vacua were stable, that would be inconsistent with quantum gravity. So one has to find a way to avoid that happening. And of course, I mean, the cheap way is just to claim that there are more instabilities in addition to the ones that we know from the standard model and so on. But the other way to avoid this to happen is to require that these vacua do not form, which is possible if there are light fermions in your theory, which are smaller than the value of the cosmological constant. So this is not unnecessary, but a sufficient condition to make sure that the standard model is explaining you or providing a possible explanation between the neutrino masses and the cosmological constant in our universe. In particular, also, if we write the neutrino masses in terms of the Higgs wave, it's relating both hierarchy problems. No, I mean, that if you happen to live in a universe with a small cosmological constant, you should also have a small electroweak scale. So it's an example, just an example to show you how these Swampland conjectures can break with the logic of naturalness, because all these fine-tuning issues might be just an artifact of not knowing what is the real landscape of parameters that are consistent with quantum gravity, so that not everything goes. And I think we should revisit our idea of fine-tuning, in which we assume that any value of the parameter should be possible. Okay, so can I have 5 more minutes? Yes?
Sure.
I mean, if I have 5 more minutes, I can finish what I wanted to say about the de Sitter conjecture, and then we can ask if there are questions. Okay, so it's going to be very brief. I just want to say a few words about this. So there is also this de Sitter conjecture, claiming that there are no de Sitter vacua in string theory. There are different versions of this, depending, like the original de Sitter conjecture, but also this TCC, which doesn't forbid de Sitter vacua in general, but only at the asymptotic regimes, and requires that the de Sitter vacua has to be short-lived. And I mean, the point is that I think it's an open question whether string theory is CERN yet, but there is also not a full-fledged top-down de Sitter construction in a controllable regime. So it's a very challenging and difficult task, but I think it's something we need to continue working on to find out what is the answer. Now, so at the moment, I mean, I don't want to say much about these conjectures because they are at a very early stage, I think, gathering evidence and everything. But it's true that we can provide evidence for a mild version of this conjecture, which is what I call the asymptotic de Sitter conjecture, which is simply claiming that indeed, if we try to approach one of these infinite field distance limits, in which we get this tower of states that are becoming light, also the potential has to behave in a particular way. In particular, this derivative has to be bigger than the potential itself, forbidding the presence of vacua. Okay, so there is always this runaway behavior. So it's sort of a generalization of the Dine-Seiberg problem that we know for the string coupling, but for any scalar direction in your modular space, so for any possible limit that you can have. Okay, and for this we can, I mean, this is something concrete that we can check in the same way that we check the distance conjecture or the weak gravity conjecture in these string theory compactifications at the asymptotic limits. Okay, so I think that at least here we can and we should make more progress. And let me just tell you a little bit what we know. So there are 2 ways to argue for this, to provide evidence. One is in relation to the distance conjecture, because, well, the idea is that also using these arguments of integrating out the states, one can think that this runaway behavior is a consequence of having these infinite towers. Okay, so it's the tower is responsible for this runaway behavior, which we can derive just by imposing that this potential has to be smaller than the species scale. But there is this derivation in this, well, the paper of Hiroshi, Kumrum, Gary, and Eram, in which they show that by imposing that the entropy of the tower has to be smaller, let me take this other pencil, then has to be smaller than the Gibbons-Hawking entropy that is just given by the Sitter horizon, and that the number of states is going to increase exponentially with the distance, as happens with the distance conjecture. Using these two things, one can show that indeed the potential for a quasi-de Sitter scenario, in which there is sort of a runaway, so it's very flat, indeed scales exponentially in terms of the proper field distance with a factor that is related to the exponential rate of the tower. Okay, I think it's not shown in any paper, but also preparing the lectures, I noticed that if one replaces here the value of the exponential rate for a KK tower and uses the species bound, one derives precisely the factor of the potential that appears in the TCC, in the Transplanckian censorship conjecture. So there is another relation between the conjectures that appear that maybe I will try to study in the future, but I wanted to mention in case someone wants to do it as well. And the other thing that I want to say is that, okay, as I said, I mean, we can gather evidence for this coming from string theory. Before these conjectures, there are multiple novel theorems for the case of classical de Sitter vacua, right? When we don't consider non-perturbative effects. And they are simply based on the scaling of the moduli. And I think that this is again related to what is the possible types of potential, the structure of the potential that arises at these asymptotic limits and how the geometry is constraining also this form of the scalar potential. So I want to remark that all these no-goes do not apply to KKLT or large volume scenario or anything like that, because in those setups, one is assuming that non-perturbative corrections can compete with the perturbative part. Okay, so if you have some non-perturbative corrections that are of the same order than the perturbative vacuums, or the W naught is very small, and therefore you generate a vacuum, but that means that you are away from these asymptotic regimes. I mean, in the moment which these non-perturbative corrections are more important than the perturbative ones, we are not talking about the same asymptotic regime that we are talking with the distance conjecture. Okay. But whenever this expansion makes sense and the perturbative expansion still works, then one can show that in this flux potential have this runaway behavior. So I had here one example, but I think I will just leave it as an exercise. This is the potential for the case of type 2A on a Calabi-Yau threefold at weak coupling and large volume. And you can show that, I mean, just by taking derivatives of this potential, that it satisfies this inequality, which indeed forces you to satisfy this de Sitter conjecture with this factor. And we have shown also that you can go to more general situations coming from F theory, so not just weak coupling, but going to strong coupling regimes, and still this seems to be satisfied. Okay, so I have also this, but let me just finish. So the other conjecture is this ADS distance conjecture, in which one can generalize the distance conjecture, not just to variation of scalar fields, but variations also of the metric configurations, so in this case. And one can show that the flat space limit is at infinite distance in this space. And therefore, the authors use this to conjecture that any ADS d-dimensional vacua should contain an infinite number of states that become massless when you take this infinite distance limit, when lambda goes to 0. And this is associated, I mean, this can be associated to or it gets entangled with the fact that in supersymmetric scenarios, it seems that we don't get any scale separation between the external and the internal space, internal dimensions. Of course, the specific, as usual, what is the specific value? What is this exponential rate? It's a harder question than just claiming that you have a light tower. So in this case, it's a strong version to really tell what this factor is, and it's just based on examples. So, I mean, also, I hope that our understanding of this will improve in the future. Okay, so this is all I wanted to discuss. So these are the conjectures that we have deal with in this series of lectures. I hope that this can serve as a pedagogical introduction to this program. Of course, I mean, there are a few more conjectures that I didn't discuss here, but I mean, who knows what will be the fate of them. And I want to draw your attention again to these connections between these conjectures, because this is something that we are discovering now this year. I think it might change our understanding of the Swampland program for the next years. Like sometimes when you have like different things that seem to be connected, like with the web of dualities, right? I mean, maybe we don't understand very well one of these dualities, but then it gets connected to another one, and then we can go to another setup in which we can try to prove it, or it's easier to understand. So I think exploring this web can be very useful for the future. And as you may notice, there is not a single approach to work on the Swampland program and try to prove these conjectures. Like I focused on coming from a string, from string compactifications and relating these conjectures to the geometry of the internal space. But there are many different approaches, so I encourage all of you to give some thoughts to these conjectures, or in general to what are the constraints that effective field theories should satisfy to be consistent with quantum gravity, because the more perspectives and approaches that we have, the better. So let me stop here and ask if there are further questions.
Well, I guess there would be lots of things to discuss, but let's thank you first for this wonderful series of lectures. So any other questions?
Thanks for the invitation. It's really an honor to give some lectures here.
Well, while people think about possible questions, let me thank here just also to Elena and the IT support at CERN, who sort of took care about the streaming and the recording and everything. And I should also mention that we would be very interested in getting feedback from the students. So either in private email or even in the chat or in Slack, just what they think and what could be improved. So just feel free to speak out. So any other questions? Okay, so let me put a provocative question. Of course, we sort of guess what the answer is. But, so one of the outputs of this would be to say, whenever you have a weakly coupled theory of gravity, it must be a string theory. That's one output.
Yeah.
This is what we believe anyway. And the critics would say, okay, you stay all the time in this framework, so no surprise that you always find, argue back, find sort of get back to the same assumptions. So the real question would be, is this really, how general is this really in the end?
Yeah, no, I mean, I think, yeah, it's a very important question to understand whether these conjectures are distinguishing string theory from other quantum gravity theories, or are general principles that should apply to any quantum gravity theory, because in the end, everything somehow is connected to string theory. And I think for that reason, it's important to have more bottom-up explanations, like based on black hole physics, or also more general proofs, maybe using ADS-CFT in terms of the CFT, regardless of whether you have a weakly coupled description. And try to find out if these arguments are convincing enough so that we think it's more general or not. And we always have some, we are restricted to string theory. At the moment, I prefer not to claim that it's completely general because I always work in string theory. So,
and for example, that most arguments are based on supersymmetry and BPSness and this kind of ideas, and all of this disappears if you go to non-supersymmetric theories. So that's really a big question.
Yeah, exactly. Getting rid of supersymmetry is a very big question. In that sense, that's why also all these arguments based more on topological abstractions, dynamical abstractions, I think might be more useful. And also, we have some non-supersymmetric string theories, like we have the SO16, cross-SO16, heterotic string theory, and so on. So I think we can also use them as playgrounds, try to understand what happens there. And so far, they are not counterexamples to these conjectures. So I think that's a nice hint. But yeah, of course, getting rid of supersymmetry is hard.
In high dimensions, simple, but say in 4 dimensions, non-supersymmetric theories, won't have modular spaces. Yeah, they will be isolated vacuum mostly.
Yeah, yes.
So how much of the arguments with long distances and so on would remain in this situation? If you could argue, that a theory might be asymptotically supersymmetric in the long run, then maybe some arguments can be. So
yeah, exactly. It would be nice if one can argue that there is a way, that you should restore supersymmetry at some point, or some misaligned supersymmetry or something like that. Which might be, also based on stability and all these issues. Maybe it's not such a crazy idea.
I guess maybe I want to make a related comment, is that so the way you pose the problem, it's exactly the way people pose the problem in conformal bootstrap, right? You want to separate from what is possible from what is not, so the statement of the problem is the same, but based on just general principles, it seems like it's not enough to derive these dramatic conjectures. So on the bootstrap side, one have to put in something else, and it's not quite clear, right? What this maybe it's modular invariance, maybe it's unitarity of black holes, but it's somehow seems like we are missing some extra constraints, which will, starting from bootstrap, all these conjectures should come out somehow if they are true, and if we impose enough constraints. So there is very far. Even though the question is the same, the status of our control is or the kind of dramatic claims is very different. So it'd be interesting, of course, to understand what is the extra somehow. What is the extra? If we just impose that there is a graviton and there is a large gap, it seems like these bootstrap equations are not strong enough. But like, what is the extra ingredient that we should put into the consistency to derive much stronger bounds?
That made my secret conjecture here.
Sorry that I think my connection was not very good.
Well, it was okay.
Okay.
So
so I think that's an excellent question. I was also thinking about it because we have the same approach, as you said, with the conformal bootstrap and with this Swampland program. So one would expect that there should be more connections and the things that we observe, and it's actually very hard to prove these conjectures on the bootstrap.
Exactly. Yeah.
Maybe it's a matter of finding a better functional at some point. I don't know. I don't discard it. But I agree. It's true that there are things, as you said, that we know that we are missing. Like, I don't know. Sometimes modular invariance seems to be important also to prove the gravity and so on. And also somehow the discreteness, I don't know, I feel of that we have in string theory. Sometimes this discreteness also plays an important role. I'm not very sure sometimes how this translates into the bootstrap program. But yeah, I don't know. I think it would be amazing if at some point we can we are able to give some proof based on conformal bootstrap of any of these conjectures, even if it's a mild version or something like that.
Let me add my secret hope, say, why I think also the whole program is sort of useful. It's a bit maybe thinking like cyber written theory. You know, you have sort of local patches in moduli space, and you can make some sort of local considerations, one loop computations, and so on. But you really cannot solve the theory. Yeah, but it's the global connectedness of the whole thing which solves this theory, and maybe you can sort of make an analogy to the whole, you know, do your picture with the different aspects of the Swampland conjectures, namely that sort of the working together of all of them creates sort of enough constraints around the circle in order then to get some real proof, you know, or some stronger statements. So it's a working together of everything which is gonna help, and it's probably not a single idea somewhere which would suddenly solve everything.
Yeah, I agree. That's a nice picture. In fact, I feel that now by studying these moduli spaces and the asymptotic limits, it feels something similar to all this bulk reconstruction that you have in ADS-CFT.
Yeah.
That's, you're wondering, okay, with all the information I have in the boundary, how much I can tell about the bulk and how much I can get deep inside. It seems that, yeah, like now we have some things, I mean, we have information about what happens when we have these approximate global symmetries and we are near the boundary, and we are trying to understand how much we can tell about the universal things of the global structure and what happens in quantum gravity in general, they are deep in the bulk, even if we cannot compute it and have an effective field theory there, right?
Before overlook it, there's a question in the chat. Can you read it yourself, or shall I read it to you?
I can read it. I can also read it out loud for the people. I have some general basic, there are no basic questions. If it's okay, it's okay, of course. Is Vasilev's gravity de Sitter still studied? What do you think about fastball? They don't satisfy entropy, but intuitive string-wise. Or maybe that is the main reason to deny them. What is your basic answer to experimentalists saying that string theory already forgotten is no such thing in LHC? Okay, there are many questions here. Well, first, yeah, I mean, about Vasilev, de Sitter, and so on, it's the same problem we discussed. Like many of these conjectures, I mean, the goal of the Swampland program is try to understand the constraints that an effective field theory weakly coupled to Einstein gravity has to satisfy. At least this is the first goal, no? Then maybe one can try to generalize it. So that excludes Vasilev gravity, just because you don't have a gap, no, to the higher spin fields. So there is no reason why these conjectures should apply there. And that's why, for example, it can be dual and you can have a de Sitter space. I mean, that's fine. I mean, the problem is to have these features when you have an Einstein gravity description.
So maybe can I follow on this question a little bit?
Yes.
Because
yes, please.
So when we say that for these conjectures it's important to have the gap, is it the reasoning? Is there intrinsic argument for every conjecture that you need the gap, or it's more like we know that all our examples when it works have big gap and therefore we do not extrapolate, or for each conjecture you have just independent arguments that you need a gap? Or
okay, so the thing is that these conjectures typically, I mean, they come together with a notion of a quantum gravity cutoff. Like they are saying that that effective field theory is fine as long as you're describing energies below some cutoff. So this notion of having some quantum gravity cutoff only makes sense in Einstein gravity. And that's why there is something intrinsic about Einstein gravity in the conjectures, in the sense that, for example, with the tower of states, I mean, there is nothing wrong with having this infinite tower of states. You can resolve that in the string theory, and you have singularities in the string theory, but there is something wrong from the point of view of the effective field theory of Einstein gravity. So that's one thing. So I really think there is something, I mean, that Einstein gravity matters. On the other hand, that doesn't imply that there is some version of the conjectures that might be more general, because in the end, if these conjectures are reflecting some quantum gravity principle, I mean, one would expect that this quantum gravity principle maybe also has some implication, even if you don't have Einstein gravity, it just takes some maybe a bit different form, or I don't know, I mean, like there is some remnant. So in that sense, it's true that when we say Einstein gravity is a bit to be conservative, in the sense that, okay, we know that when we have Einstein gravity should apply, we don't know yet what is the right form when there is no Einstein gravity, even if maybe there is one. And one example of this is, for example, this distance conjecture, right? Like the distance conjecture is tied to Einstein gravity in the bulk, but still it seems that we can have a version of the distance conjecture in the CFT, which seems to be valid for any CFT, regardless of whether there is an Einstein gravity dual or not. So I mean, there is a version that still applies there. But yeah, one has to be careful when you extrapolate how you do it. Yeah.
Thanks.
What do you think about fastballs? I don't know. I think I'm not the right person probably to give an opinion that is worth it. So let me not to do it, since this is recorded. Yeah. And what is your basic answer to experimentally saying that string theory is already forgotten? I would say, I mean, I've always said that, I mean, string theory is true that is very linked to the existence of supersymmetry, but to the existence of supersymmetry, first of all, in the worldsheet, when we want to have fermions, not so clear in the target space, but even if we have supersymmetry in the target space, it's not necessary at all that we have supersymmetry at low energies. And in fact, I think I would say that from the point of view of string theory, I think what is more natural is that supersymmetry is broken at a high scale. And what is difficult is always to engineer these hierarchies in which you break supersymmetry at a very small scale. So I think that if you come from string theory and you forget about the naturalness problem, the electroweak hierarchy problem, and all these things, the more natural thing, without fine-tunings or anything, is that you break supersymmetry, for example, with fluxes in the bulk, and then this has a supersymmetry breaking scale, which actually scales, I mean, if you take large volume and so on, scales like 10 to the 14 GeV or so. And this is like putting everything order one factors. So I would say it's the opposite, like you have to work hard to have low energy supersymmetry. This is telling us that maybe the role of supersymmetry is not to provide a solution to the electroweak hierarchy problem, but maybe the role of supersymmetry is to make sure that our vacuum is sufficiently long-lived, like to explain some stability of the vacuum or other features. And it could still be necessary to have supersymmetry restored at a high scale, which would be very interesting. So yeah, that would be my answer, that string theory is not forgotten, because in fact supersymmetry is more likely to be broken at a high scale. Any other question?
Okay, I think we can conclude the school. I hope next year it will be possible again to have it in the physical presence, not virtually, but who knows. So anyway, we are pretty glad that things work so well in this virtual way.
Yeah, so let me, before you close, also I'm the last speaker, so I don't want to forget to thank, I mean, we should all, even if in our houses, thank all the organizers for this wonderful winter school. The only thing I regret is indeed not to be able to be there, but I mean, thank you so much for organizing this and the invitation also to give the lectures.
Okay, thanks to the speakers in particular. So, who's switching it off? Sasha?
Yeah, I can switch it off, and yeah, as Wolfgang said, also would like to join thanking the speakers for fantastic lectures. It was really great, and of course we all enjoyed. So thank you very much, and thanks for the participants to also joining. Hope that you enjoyed the school.